Today we're going to be taking a look at inverse trig functions. So before we talk about inverse trig functions, I want to remind you a little bit about just inverse functions in general, how to find them, and the notation. The notation that is generally used for inverse functions is this notation that looks like an exponent with a -1. But remember that if that notation is on a function, it does not mean reciprocal. This is not 1 over f of x. Okay? And the difference is because f is a function. If this notation is on a number or on a variable, it certainly does mean the reciprocal of that thing, whatever that is, but not if it's a function. All right? So, notation. Now let's recall how to determine the equation for an inverse function, the process to determine what the equation is of an inverse function. Let's find the inverse of this function. Okay, so to find the inverse of a function, we switch the x's and the y's, and we solve for the new y. So g of x, that's our y. I'm going to replace the y with an x. I'm going to replace the x with a y. If there were more x's over here, I would replace every x with a y. There should only be one y if this is a function. So anyway, so I'm going to switch. I'm going to replace the y with an x. And I'm going to replace that x with a y. And now we solve for our new y. So there's our y. I'm going to begin by adding 2 to both sides. So x plus 2 is this function, is this part. Now I'm going to multiply both sides by that 5. When I multiply both sides by 5, I'll get 5x plus 10 is ln of 3y minus 7. And now we're looking for y. We're trying to solve for y, so to get rid of this ln, we take e to both sides. E to both sides. And when you take e to both sides, on the left-hand side, I just have e to the 5x plus 10. If you want to keep that in parentheses, you can. Otherwise, just be careful. Make sure that 10 does not look like it's being added to the e function. Make sure that 10 is being added to the 5x. And that is equal to just the argument. Continue solving for y, add 7 to both sides. And lastly, divide by 3. Dividing by 3 is the same thing as multiplying by a third. I might just write it like that. Like that. So we have found our inverse function for g. Inverse g is a third of e to the 5x plus 10 all plus 7, like that. Alright? So that's the process for finding an inverse function, and that is exactly what we will do to find the inverse functions of any trig function. Okay? So recall how to determine if an inverse is a function. Okay? An inverse of a function is itself a function. So the inverse of a function is a function if the original function f passes the horizontal line test. It's been a while since we've done that, but that is true. So f, let's think of maybe this is f of x is equal to x cubed. It is itself a function because it passes the vertical line test, and its inverse is a function because it passes the horizontal line test. So its inverse would be the cube root of x, and that graph would look like that. It has symmetry with respect to the line y is equal to x. It should, if I'd graphed it right. It would have symmetry with respect to the line y is equal to x. I should have gotten a little bit flatter there. Okay. Alrighty. So if a function passes the horizontal line test, and it itself is a function, then f is said to be 1 to 1. It's very unlikely you remember that, but we did talk about that. That just means it is itself a function, and it passes the horizontal line test. We call that 1 to 1. So let's take a look at sine. Here's the graph of sine. And it never stops. I only drew part of the graph. So there's the graph of sine. It is itself a function because it passes the vertical line test. Is its inverse a function? Absolutely not. There are horizontal lines that pass through this graph more than once, so it does not pass the horizontal line test. So right now, no, this is not a function. The inverse of sine x would not be a function, but we need it to be a function. And because we need for the inverse to be a function, we are going to restrict the domain of sine x. We're going to make sine x, we're going to restrict it so that sine x is 1 to 1. So the question is, where do you restrict it? Where do you cut it to where it would be 1 to 1? We only want one section where it's 1 to 1. So where would that be? Well, it would not be over here because that would not pass the horizontal line test. It could be here, going from negative 3 pi over 2 to negative pi over 2. It could be from negative pi over 2 to pi over 2, or from pi over 2 to 3 pi over 2, or 3 pi over 2 to 5 pi over 2. There are lots of sections that we could restrict this to where sine x would be 1 to 1. So, which one should we use? Which one is the best? Well, this is arbitrarily done. However, somebody a long time ago said we need to keep the section that is closest to the origin, closest to x is equal to 0. So we arbitrarily restricted the domain to be from negative pi over 2 to positive pi over 2. And I say that that is arbitrary. However, it is conventional. It is. This is where we restrict it to. This is where not just we restrict it to, it's where everybody restricts it to. If you pull out your calculator, it restricts it to there. Okay? So, sine x is still the whole thing. However, when we restrict its domain, the inverse of sine is a function, and that's what we wanted. So we restrict the domain of sine x so that the x values are as close as possible to 0. So the domain of sine x that is used for inverse sine of x is negative pi over 2 to positive pi over 2. That's inequality notation. If you prefer, you can write that in interval notation, and it would look like that. That means that every value of inverse sine x, every value has to be between negative pi over 2 and pi over 2. Every value. Okay? So you will never have a value of sine inverse that is above pi over 2 or less than negative pi over 2. Okay? So this is the notation for an inverse. There is another notation that we use for the inverse of a trig function, and that is this arc prefix. So arc sine of x is sine inverse of x. They mean the exact same thing. You need to know both notations. All right? They're both used, so know them both. this is the graph of inverse sine x right here. So remember that for sine x, this is the point pi over 2, 1. This is the point 0, 0. This is the point negative pi over 2, negative 1. On the inverse, those will be switched. So 0, 0 should still be on sine inverse. The point 1 pi over 2 will be on the graph of sine inverse. And the point negative 1, negative pi over 2, will be on the graph of sine inverse. And it is. This is the point 1 pi over 2. This is the point negative 1, negative pi over 2. And 0, 0 is still there. Okay, that's the graph of sine inverse. It does not do this. It does not. It only is right there. If I graphed it on my calculator, we can confirm that. Sine inverse of x. Right there. It stops. It does not continue. All right. So, how do we find some values? Let's find some values of sine inverse. So when you see sine inverse of a half, in your mind, here's what you should be thinking. Sine of what is 1/2? So we switch the x and the y, right? So sine of what is a half? Well, pi over 6. Sine of pi over 6 is a half. So that's it. That's it. So sine inverse of a half. Okay, so notice that pi over 6 is indeed between negative pi over 2 and pi over 2. It is indeed between there. So if we go to a half on this function, right there would be pi over 6. Okay, what would arc sine of square root 3 over 2 is? So remember, you're thinking to yourself, sine of what is square root 3 over 2? We have to know our unit circle values very, very well, because now we're going backwards. So arc sine of square root 3 over 2, sine of what is square root 3 over 2? That needs to be pi over 3. Okay? What if you have a negative argument? So what if we go negative? Well, our answer is going to be negative, right? Our answer has to be negative. So sine of a negative square root 2 over 2. So in your mind, you're thinking sine of what is a negative square root 2 over 2? Well, you might be thinking, okay, well, sine of what is negative square root 2 over 2? There are two. There's one at 5 pi over 4, and there's one at 7 pi over 4. Those both give me an angle that makes sine negative square root 2 over 2. However, both 5 pi over 4 and 7 pi over 4 are larger than pi over 2. We do not want to go greater than pi over 2 for an inverse sine. We cannot be greater than pi over 2. So we cannot do this if we're finding an inverse sine. We cannot. Instead, we go backwards, make it negative. So this would be a negative pi over 4. Negative pi over 4. Okay, arc sine of a negative 1/2. Well, sine of what is a negative 1/2? It'll be backwards. So it'll be a negative pi over 6. So sine of 1/2 is positive pi over 6. Sine of negative 1/2 is negative pi over 6. Sine of square root 2 over 2, that's just in the first quadrant. Sine of what is square root 2 over 2? Pi over 4. So sine of square root 2 over 2 is pi over 4. Sine of negative square root 2 over 2 is negative pi over 4. Alrighty. arcsine of negative square root 3 over 2 will be a negative pi over 3. Okay, so for arcsine, if you're talking about the unit circle, if your argument is positive, you're just in the first quadrant. If your argument is negative, you're in the second quadrant. Arcsine is right here. Okay? So what about arcsine of 0? Arcsine of 0. So in my mind, I think of the sine curve. I think of the sine curve, and sine does this. But for inverse trig functions, we restrict it to be between negative pi over 2 and pi over 2. So sine of what is 0? Sine of 0 is 0. The other way you can do that is think on the unit circle this way. Okay. At 0 radians, sine is 0. Okay. Alright, sine inverse of 1. Well, in my mind, I think of the sine curve. And right here, sine is 1, and that is pi over 2. Or you can think, where is sine 1? Sine is 1 at pi over 2, right there. Arcsine of negative 1. Negative 1 would be negative pi over 2. Got to know our unit circle values very, very well. Okay, now let's talk cosine. Here's the graph of cosine. Are we going to restrict it also to negative pi over 2 to pi over 2? No, we're not, because it will not pass the horizontal line test. So where should we restrict it? We should restrict it from x is equal to 0 to x is equal to pi. So for arc cosine, for inverse cosine, we will not have any negative values. Everything will be between 0 and pi. On the unit circle, between 0 and pi for arc cosine. Okay? Alright, so the domain that we restrict this one to is 0 to pi. Every value will be between 0 and pi. Every value. Every one of these values will be between 0 and pi, so no negatives. Here's the graph of arc cosine. That's the graph of arc cosine. And I could show you on the calculator, but hopefully you trust me. That is the graph of arc cosine. It stops right there. It does not continue, because then it would not be a function. And this way, it's a function. All right. Arc cosine of a half. So just like we did for sine, you're asking yourself, cosine of what is 1/2? And you need to know that that is pi over 3. Cosine of pi over 3 is a half. Arc cosine of square root 3 over 2. Cosine of what is square root 3 over 2? Well, that will be a pi over 6. Got to know those really well. Okay, cosine inverse of negative square root 2 over 2. It's negative. It's negative. So in my mind, I'm thinking for our cosine, I need to go to quadrant 2 if the argument is negative. So this is the pi over 4 angle in quadrant 2. So that will be 3 pi over 4. Our cosine of negative 1/2, still in the second quadrant, but it's the pi over 3 angle in the second quadrant, so 2 pi over 3. Cosine inverse of square root 2 over 2 is just pi over 4, first quadrant, easy peasy. But if it's negative, we need to stick it in the second quadrant. This is the pi over 6 angle in the second quadrant, so that is 5 pi over 6. Now let's do it on the axes. On the axes. So on the axes, what I do, and this is not the way you have to do it, but what I do is I think of one section of cosine. Cosine starts at 1 and it does that. And right here we're at pi. Here we're at pi over 2. Here of course we're at 0. So our cosine of 0, where is cosine 0? Cosine is 0 at pi over 2. So I'm asking myself, cosine of what is 0? Pi over 2. Cosine of what is 1? Well, cosine of 0 is 1. Cosine of what is negative 1? Cosine of pi is negative 1. So that is arc sine and arc cosine. Let's take a look at arc tangent. So once again, let's think of the graph of tangent. How should we restrict its domain? Well, for its domain, we're only going to keep one little arm of tangent. Everything else we're going to ignore. So we are going to restrict the domain once again, just like arc sine. We're restricting the domain from negative pi over 2 to pi over 2. Negative pi over 2 to pi over 2. So every value of arctan, of tan inverse, is between negative pi over 2 and pi over 2. This is the graph of arctan. It's one arm. So unlike arc sine and arc cosine, it continues forever. Its domain is everything. Remember that for inverse trig, for inverse functions in general, the domain of f is the range of f inverse, and the range of f is the domain of f inverse. So the range of tangent is all real numbers. That means the domain of inverse tangent must be all real numbers. We are restricting the domain of tangent to be between negative pi over 2 and pi over 2. And I just realized I should not have included these boundaries, because it will never reach pi over 2 and negative pi over 2. I'm glad I came back to this. So do not include those for this. So this is the restricted domain. That means that that is the range. So the range of inverse tangent, the range is between negative pi over 2 and pi over 2. Okay, so what is inverse tangent of square root 3? Well, I know that tangent of pi over 3 makes square root 3 over, makes square root 3. 1, 3, 1, 3, right? So this is pi over 3. What about arctan of a negative? For a negative, for arctangent, everything is between pi over 2 and negative pi over 2. So it's either up here or down here. So if it's negative, just like arc sine, it's just going to be negative of whatever angle makes tangent square root 3 over 3. And we should know that that is pi over 6. So negative pi over 6. Inverse tangent of 1 is the angle that makes tangent 1, and that's just pi over 4. And arctan of negative square root 3 will be a negative pi over 3. Arctan of negative 1, negative pi over 4. That's down here in the fourth quadrant, but we go backwards to get there. We do not go around. Do not go around, because that would make us larger than pi over 2. Arctan of 0. What angle makes tangent 0? 0. Goes right through the origin. We can do something with arctan that we could not do with arc sine or arc cosine. We can find a limit. What is, as x goes to infinity, what is arctan approaching? Arctan is approaching pi over 2. What about as x goes to negative infinity? Arctan is approaching negative pi over 2. Couple of limits. All right. Let's touch on these other inverse trig functions. the domain restriction for arc cosecant is the same as that of sine inverse, arc sine. Okay? Negative pi over 2 to pi over 2. This is because, just like tangent and sine, cosecant is an odd function. Okay? These are all odd functions. They have symmetry with respect to the origin. The other functions, though, do not have symmetry with respect to the origin. Okay? How should we restrict the domain of cotangent? Here's cotangent. Okay? Here's the graph of cotangent. So we're going to restrict the graph of cotangent to be from 0 to pi, but not including 0 and not including pi. Just 0 to pi. Okay? So, here's a nice visual I made to remember inverse trig values. Inverse trig values. Anything if the argument is positive. If the argument is positive, quadrant 1, just positive, it's the angle, you're done. If it's arc cosine of a negative, arc secant of a negative, arc cotangent of a negative, you come over here to quadrant 2. If it's arc sine of a negative, arc cosecant of a negative, or arc tangent of a negative, you go to quadrant 4. However, you go backwards to get there. It's going to be a negative angle to get there. You do not go through quadrant 3 to get there. Do not go through quadrant 3 to get there. Alright, so this is, I call this the black hole for inverse trig functions. Nothing goes there. Nothing even goes past there. So you can go to quadrant 2, but you cannot go around through quadrant 3 to get to quadrant 4. Alright? So for inverse trig functions, none shall pass. Okay? A little Monty Python and the Holy Grail reference there. Anyway, if you haven't watched that, it's a hilarious movie. Okay, so let's do arc sine of a half. Let's do just a bunch of different examples here. So arc sine of a half. What angle makes sine a half? That's what you're thinking. Sine of what is a half? 1/2 is positive. So we're just in quadrant 1. It's the angle that makes sine a half. Pi over 6. Sine of 5 pi over 6 is also a half. But remember, arc sine is never in quadrant 2. Arc sine is only in quadrant 4 or 1. Okay? What about arc cosine of negative 1/2? Well, arc cosine, if it's negative, lands in quadrant 2. So what angle makes cosine 1/2 in quadrant 2? That is the pi over 3 angle in quadrant 2, and so that is pi over 3. Pi over 3 is the reference angle there in quadrant 2. Okay, arc cosecant of negative 2. First I do my quadrant. It's arc cosecant, so I know my answer is going to be negative. It's going to be down in quadrant 4. After that, I think, okay, this is the same as arc sine of a negative 1/2. Arc cosecant of negative 2 is arc sine of negative 1/2. This is the angle that makes cosecant negative 2, and that means it's the angle that makes sine negative 1/2. So that's going to be the pi over 6 angle down in quadrant 4. Okay, here we have a little combo. I'm going to start inside, of course, and find that, and then I'll take secant of whatever my answer is. Arctan of square root 3. First quadrant, this is just pi over 3. So now we have secant of pi over 3. What is secant of pi over 3? Well, that is the same as cosine. It's the same as 1 over cosine of pi over 3. Cosine of pi over 3 is a half. Flip a half, and we get. Okay. So, let's see. Next step. So I have cotangent. I'm going to go inside and do that. What is cotangent of 5 pi over 4? Cotangent of 5 pi over 4. Well, it's a pi over 4 in quadrant 3. Cotangent is positive in quadrant 3. So this will be a positive. The reciprocal of tangent of pi over 4, that's still just 1. So positive 1. What is sine inverse of 1? Sine inverse of 1. In my mind, I think of the graph of sine, and it reaches 1 at pi over 2. This is pi over 2. That's how I do that. Okay. What is arc cotangent of a negative square root 3 over 3? Well, it's arc cotangent. Arc cotangent falls in quadrant 2 if the argument is negative. So arc cotangent of what is square root 3 over 3? So in my mind, I know if this was a tangent, this would be a pi over 6. It's not a tangent, it's a cotangent, so it's the other one. It's not the pi over 6, it's the pi over 3. So it's the pi over 3 over here in quadrant 2, 2 pi over 3. Number 7. We'll come inside. Inverse tangent of a negative square root 3 over 3. It's inverse tangent, so we go down backwards into quadrant 4. And so that's going to be a negative pi over 6. And now we need tangent. What is tangent of a negative pi over 6? Well, we're in quadrant 4. Where tangent is negative, and it's a pi over 6, so it is square root 3 over 3. Tangent of inverse tangent of negative square root of 3 over 3 is negative square root 3 over 3. That shouldn't be very surprising to you. Okay? What about sine of arcsine of square root 3 over 2? What is arcsine of square root 3 over 2? First quadrant, sine of pi over 3 is square root 3 over 2. And so then sine of pi over 3 is square root 3 over 2. A function of its inverse is always going to yield the same thing. Is that true for every inverse of the function? No, it's not. And here's why. Because of the restricted domain. Sine of what is 4 pi over, or sine of 4 pi over 3 is what? So 4 pi over 3 is down in quadrant 3. Sine of a pi over 3 angle is going to be a square root of 3 over 2, but this is going to be negative because sine in quadrant 3, from all students take calculus, sine is negative there. And now arc sine of a negative square root of 3 over 2, now it's an arc sine, so we go down, we go backwards into quadrant 4. This is going to be a negative pi over 3. So when you have the inverse trig function outside and the regular function inside, it's not necessarily the same. It might be the same, but it might not be the same. But if you have your regular function first, then that will always be the same. All right? Okay, what about secant of pi? Secant of pi. Okay, that is 1 over cosine of pi. Well, cosine of pi is negative 1, so secant of pi is negative 1. So we need sine inverse of a negative 1. Sine inverse of a negative 1. In my mind, I think of the graph of sine. The graph of sine does that. and it's -1 at -pi over 2. Arc cosine of 0. Arc cosine of 0. What angle makes cosine 0? That is pi over 2. In my mind, I am thinking of the graph of cosine. It is 0 at pi over 2. So arc cosine of 0 is pi over 2. So now what is tangent of pi over 2? Well, tangent of pi over 2, the graph there has an asymptote, right? This is undefined. Okay. Cosecant of 5 pi over 3. Well, cosecant of pi over 3 is 1 over sine of 5 pi over 3. Sine of 5 pi over 3, 5 pi over 3 is down in quadrant 4. Sine is negative, and it's 1 over sine of 5 pi over 3 is square root of 3 over 2. So cosecant will be the flip of that, so 2 over square root 3. Or 2 square root 3 over 3. Now we need arc secant of that. Arc secant of that. Okay, well, it's negative, and it's an arc secant. That means I go over here into quadrant 2 for arc secant of a negative. Now, 2 over square root 3, that means cosine is square root 3 over 2, so that means this is the pi over 6 angle in quadrant 2, so 5 pi over 6. Okay, that is the inverse trig function lesson. Okay, these can get a little complicated. They definitely take more time than unit circle values, even though we are definitely using the unit circle values. They definitely take more time though, so take your time, get these right.